Okay, let's settle down. So last class, what did we look at? Okay, let's settle down, guys. Okay. So we looked at a feedback system. VE, right? So we looked at a feedback system where you had an integrator, omega u times, right? Omega u was the slope of the integrator, correct? And you tried to make an amplifier of value k, right? And we found out the bandwidth of the amplifier was approximately omega u over k, correct? We put in a sinusoid, looked at what happens when the linear phase approximation is valid, correct? And the amplitude, both. And we found this was the condition, that the frequency needs to be less than, actually much less than omega u over k, but we say up to omega u over k, it's a pretty good amplifier. Not the best one, close to omega u, but it's pretty decent. Okay? And in other words, if you put in a frequency, we first analyze the steady state for DC, then we put in a sinusoid, right? So if you put in a sinusoid which is close to this, it will settle in a few time constants of this, right? Even if you put in the sinusoid, it's very similar to the steady state. There's not a lot of difference. Okay? Okay, so now let's just plot that. So if you plot just the integrator, open loop integrator, what's that going to look like? It's just going to be a straight line like this. This is just the integrator alone. Okay? So your amplifier is going to look something like this. Okay? With this gain being k, the low frequency gain being k, and the, okay, so for the original one, for the integrator itself, it was omega u, correct? Let's quickly find out what it will be for the closed loop case, right? We don't know that it's going to be the same as omega u. So this, right now we are just plotting the magnitude. Let me do it here. This was the magnitude, right? K over root of 1 plus omega squared over omega u over k the whole squared. Correct? So you're going to equate that to 1. You want to find out when that crosses the x-axis. What does this give you? Omega u over k, so you get k, is this right? K squared minus 1, correct? Is this right? So this happens actually not actually at omega u over k. The closed loop actually crosses the x-axis, that is has a gain of 1 of 0 dB at omega u over k times root of k squared minus 1. Or you can write this as one minus 1 over k squared. If k is even moderately large, you can approximate it to be omega u. Okay, if k is even like 5 or 10 or something like that, it's pretty close enough to omega u for our, for what we are concerned with. Okay. Now suppose you want to build an amplifier with a larger gain, with a different k, then you would be doing something like this. Sorry. Okay, you'd have something which looks okay. You'd have something which looks like the blue curve, right? Which means obviously now your omega k is larger, so omega u over k, which is k prime. So omega u over k prime is smaller, and that's this point. That's the bandwidth of the amplifier itself, correct? And again, for a different k prime, it will again cross the origin very close to omega u. Okay? Okay. Now given an amplification k, so let's say you want to build an amplifier k. Okay? What would you do? If you want to maximize bandwidth, what do you do? Obviously there is only one way to do it, which is to increase the integrator speed. Okay? So that is where your circuit design concern comes, right? So in a given process you want to build a very, very fast integrator. Now that has other obviously process related concerns. Okay, we'll come to that later. I think later in the course you'll anyway be building these circuits as part of your op amps. Okay? At that time you'll see that for a given technology, how do you build the fastest integrator you can find. Okay? But suppose you want to increase, let's say in a given technology, if you want to get a faster integrator, what that means is you'll have to burn, typically you'll have to burn more power to get a faster integrator. Okay? So let's just write down whatever we found. We have tau, we have the bandwidth omega naught, and we have the pole. We compared it with a simple RC, so the time constant was k over omega u. 3 dB bandwidth, omega u over k. And of course the pole is at minus omega u over k. Okay? So yeah, so this is for a first order system. Now let's see what will happen. We'll take the same first order system. We'll add a little bit of delay in the feedback path. Okay? And we'll see what happens in that case. Let's go back, take a step back and try to look at it in the time domain. So I know you guys have used I think the analogy Dr. Nagendra has used is the speedometer, right? You have a person who's trying to accelerate, is that right? Is that the analogy? Okay, so we'll use the same analogy. So let us say this is the target value of speed. Okay? This is the target value of speed. Now suppose somewhere in the feedback path, okay, so in the case of a person who is trying to reach a particular speed, it could be either the electronic circuitry of the speedometer itself, it could be the reflex of the person who is trying to measure the speed and change the accelerator, but there is actually it doesn't matter, you can combine them all into one full delay. And so what do you think is going to happen in the time domain? So he's trying to increase, right? Earlier we looked at what happens for a first order system without any delay. What do you think is going to happen? Why? Correct? He has already? Correct. So in other words, let's assume there is a error, let's say there is a delay TD, and in the feedback it looks as if your speed is actually increasing at this rate, okay, even though you are actually increasing it from t equal to 0. What is this? What is the difference between the target value and this? That is the error, correct? Okay. So now let me draw this in a different color. So obviously by the time this guy has reached the target value, you would have overshot, and Similarly, at some point of time, you're going to realize you're going too fast. You're going to apply your brakes. So which means your speed is going to reduce. So you'll try to reduce. But again now, in that speed reduction, there is no delay in the feedback. Correct? So you could undershoot. You could very well undershoot. Okay, so you get something like this. Does everybody see that? Okay, this is obviously a very exaggerated case which we are showing. But we'll see today what happens when for different values of delay. Okay, but basically you could see something like this. Okay, now suppose you want to reduce this overshoot. What would you do? What decides the amount of overshoot? TD. Anything else? Obviously, the slope at which you are accelerating, the speed with which you are accelerating, right? Now, if you take a second case, if you start accelerating very gently, okay, by the time your error has reached 0, you wouldn't have overshot a lot, okay? So which means you could get something like this. Let's assume for now that it's going to settle down. We'll see what happens. But you could very well, overshoot just a little bit and eventually settle. Does everybody see this? Okay? Okay. So now, obviously so now obviously the amount of overshoot depends on the speed at which you are accelerating and TD. Now if TD is large enough, or maybe your speed is too fast, you could actually get stuck in a whole case where you could just rise so much, and then by the time you have realized your error, you start coming down, and then you overshoot down all the way maybe to 0, and then go back and forth. You could see a case where you could just be oscillating between 0 speed and some very large speed. That is obviously a case of instability. Correct? Your system is unstable. Obviously you never reach your final value, because now once you have reached back to 0, the same procedure is going to start again. Right? Right? Okay. So obviously we can see that we want to reduce omega u for stability. Okay. Now obviously you can see, well, not so obvious, but from what we did before, remember that the bandwidth of the system depends on omega u. It's omega u over k. Okay. Now for increasing the bandwidth for better performance, you want larger omega u. Now for stability, you want to reduce omega u if you have a time delay. And remember, time delay is inherent in any system. Okay. Now the time delay, if you move to faster and faster processes, you have, so what is typically, what could TD be caused by in an electronic circuit? Let's say if you have a feedback, what could be the source of TD? Parasitic capacitance. You need to charge some capacitance at the feedback node. Okay, that is your fundamental limitation. If you go to finer and finer processes, your parasitic capacitance keeps reducing. Remember, we found that parasitic capacitance goes down when you scale the process. Okay, so in other words, your TD actually scales, is a function of a particular process, and if you go to finer and finer process, your TD can keep getting smaller and smaller. Okay, so which means the restriction on omega u keeps getting easier. Okay, if TD is a problem for stability. Okay. Okay, so now let's go back to your block diagram and try to analytically do it. So last time we wrote down the differential equation for the system. Let's do the same thing here. Right? Okay. What is this? This is nothing but V of t over k. What is this? T minus Td over K. Correct? So now the error voltage Vi of t minus 1 over k Vo of t minus Td. That is your error voltage. Right? And through the integrator we know what the relationship at the input and output are. This is the error voltage, right? Because it's an integrator. Okay? First of all, what do you think will happen if you have a DC case, DC quantity? Let's say Vi of t was DC, was a fixed quantity. We'll do the same thing which we analyzed for a normal, for a single without, first order system without delay. So let us say Vi of t is some DC, maybe even, let's say it's DC. What is going to happen? What will be Vo of t be? After a long time, what will it be? You expect it to reach k times Vi of t, as long as there is no instability. Okay, let's assume there is no instability for now. So that is fine. Okay. Now, without Td, you knew. So now let's say we want to find out the solution to this. Without Td, you knew what would happen. Okay, without Td, you know there is some exponential solution. Okay. In fact, we'll also do one more thing. We'll also assume that, in fact, what we'll do is, so we'll assume, let's say that Vi of t looks something like this. There is a steady state before 0, and at t equal to 0 it goes to 0. So that makes things easier. Okay, otherwise obviously now the solution of this becomes easier if you have some constant value for Vi. Okay, that's why we are doing this. So let us say this is 1 volt. Okay, and at t equals to 0 it goes to 0. So this is your new differential equation. Okay. Now for the case without Td, what do we know? What did we find out? If you set Td to 0, this is your old differential equation we wrote last time. Okay, there's no difference. Right? We did exactly the same thing. Okay. What do you think is going to be the solution for this particular e power? Why do you think that is going to be the solution for this? If Td is 0, we know it is some exponential. What is the case when Td is not 0? That's what we want to find out. Let's say you want to find out the solution to this. What form can the solutions have? So what does this tell you? First of all, why don't we take a look at this equation? It's telling us on one side we have the derivative of V0. That happens to be the same as the voltage but a delayed version. Correct? What kind of function has that form? Okay, so definitely sine and cosine have that form, right? Because you know that if you delay a cosine you get a sine, and similarly derivative of a cosine is a sinusoid, right? Forget the scaling factors, but you know you get sinusoid. Similarly for the sine also. So definitely one set of solutions are sinusoids. What else? Can you have any other function? Sorry? Yes. Okay, so you can have a distinct linear combination of sinusoids, right? Okay. Anything else? Actually, okay, you're right. Of course, you can actually solve this, but normally the way I don't know, have you solved these kind of differential equations maybe in high school or something? Typically, I mean, or in here, right, in the first year or something? Or no, just right now? Oh, I see. I thought you would have, how many courses of mathematics do you take? 4 courses, right? One of them must have been linear differential equations. Sorry? Oh man, okay. Okay, I didn't realize that. So we had, everything, when I did it, we had to do everything. Okay, we had 4 courses and we had to do everything. Okay, so some of you have not done linear differential equations. I think you should do it, right? It's kind of a very, very basic thing you need for many systems. But anyways, let's come back to this. Do you think an exponential can actually satisfy this? Why? Because, sorry? No, I know, but obviously there is a delay here. So what do you do about that? In reality, an exponential can also solve this because a delayed exponential, let's say e power j omega t minus td, is just a scaled exponential, right? You can separate the arguments in the power and take it as a scaling factor, correct? So one type of solution will also be an exponential in this case also. Everybody sees that? Okay. So you have 2 sets of solutions. Okay. So we'll start off with exponential because we've already done it before. It's a little bit easier. Okay. So we'll start off with exponential. So we'll assume that the solution of some form e power sigma t. Okay. We'll find out what sigma is. Obviously we have to solve for sigma now. Okay. We'll assume that v naught of t is something e power sigma of t. Now we need to find out what the sigma is so that we find out what v of t is. Okay. So we'll substitute this back into the equation and solve for sigma. Right? Everybody sees that? Okay. What is dv naught by dt? Sigma e power sigma t. Okay. Rather, this should be equal to minus e power sigma t times e power minus sigma t d over k. Correct? So we'll just rewrite this. Okay. So obviously e power sigma t can never be 0. So you can get rid of that unless sigma is minus infinity. Okay. So this gives you sigma plus omega u over k e power minus sigma td is 0. Okay. Now obviously now this thing is much more difficult to solve because this is an obvious nonlinear like a transcendental kind of equation. Right. So it's much more difficult to solve. So we'll make some substitutions and try to bring it to a more normalized form. Okay. And then we'll try to do it graphically. That's quite often that's the easiest and most intuitive because then you can see what happens when you vary certain terms and so on. Okay. This is our term. So now I'm going to say I'm going to define a new sigma prime, a normalized sigma prime, which is sigma over omega u over k. I'm going to define a tau, which is omega u over k times td. Okay, so in other words, now both sigma prime and tau are dimensionless, right? Because one is tau is omega u times td, which is dimensionless. Similarly, sigma over omega u by k is also dimensionless. So now we are going to rewrite this equation as sigma prime plus e power okay. So all I have done is I have multiplied and divided by omega u over k in the power term, and the first term becomes sigma prime, the second term becomes tau d times omega u over k, which becomes tau, sorry, td times omega u over k, which becomes tau. So that is the second one. The first one you just have to multiply throughout by k over omega u, and it becomes this. Everybody sees that? Okay. So let me call this f1, function f1. Okay. So your equation is basically f1 plus f2 is 0. f1 of sigma prime plus f2 of sigma prime is 0. So what we'll now do is we'll plot each one of these, plot the sum, find out where it goes to 0. Okay. Okay. So what is the first? If you're going to plot f1 as sigma prime, what is that? It's just a straight line, right? Yes? Why not? Why can't it be negative? What do you mean by stable solution? What was your old sigma? If you set tau d equals 0, what is sigma? If you set tau d equal to 0, which is our original case, what is sigma? It's actually minus omega u over k. In other words, sigma prime is minus 1. Okay, so that is actually a stable case, right? So you're right in the sense that it actually has to be negative, because first of all, if sigma is positive, both these terms are positive, so you can never have a solution. So a real solution would always have sigma less than 0, first of all. Okay, so let's try plotting both of these functions. So this is f1 of sigma prime. f2 of sigma prime is basically e power minus sigma prime tau. It's going to look something like this. So obviously for negative sigmas it's going to blow up. For positive sigma it's a decaying exponential. What is this point? 1. Correct? So what is the sum of the two going to look like? So for very large positive sigma primes, it is obviously going to tend to this. Okay. What else do you know? You know it has to pass through this, because at that point this is 0. Okay. Certainly going to pass through this. What happens when sigma prime is very large negative value? It is going to tend to this. Going to tend to this exponential, right? So what you will find is you will get some function like this. Okay. What I want all of you to do is go back and try to plot this in MATLAB, or I don't know, Mathematica, whatever, any kind of either symbolic or function plotting tool. Okay. I want you to plot these functions, these two functions and the sum of the two, and try to see what happens to the roots. After today's class, you can also try varying TD, try varying omega u, find out how it behaves. Okay? Okay? First of all, it seems like there are two solutions. Okay? We'll call this sigma 1 prime and sigma 2 prime. Okay? This will be a general case. Okay, we'll go on to find out what specific cases are there. This will be a general case. Correct? So you'll have sigma 1, sigma 2. So once you get, now if you have, you can solve it analytically, you can solve it graphically, but for any general case you can find out sigma 1 and sigma 2 because you know the two functions. Once you are given omega u, k and so on, you can find out these two functions. you can solve the differential equation or plot it graphically, whichever method you prefer. Find out sigma 1 prime and sigma 2 prime. Once you do that, you remove the normalization, you can find out sigma 1 and sigma 2. Okay? Once you get that, you get the expression for VO of t. Okay? Now that you have two solutions, what will VO of t be? A general solution for VO of t, what will that look like? It will be a linear combination of the two. Okay, it will be alpha 1 times the first exponential plus alpha 2 times the second exponential. Correct? How do you find out these two guys? Alpha 1 and alpha 2? Put it back into the equation and so basically you're going to apply the boundary conditions for the function and then solve for alpha 1 and alpha 2. So once you know sigma 1, sigma 2, you're going to apply certain boundary conditions. Okay? Okay? Now let's say your original case, when TD was 0, V out looked like this. Okay? So you have two cases, right? Depending on, sorry. So in the case when, in the original case, when TD was 0, this was minus omega u over k. Okay? What do you expect? If you have delay, do you expect the sigmas to be larger or smaller? Do you expect it to be faster or not faster? Why? Okay. No, let's go back to your, you solve this, right? For sigma 1 and sigma 2. What do you expect? Would these be, okay, so what is sigma prime corresponding to the case with no delay? So sigma is omega u over k. We normalize it with omega u over k. So sigma is minus 1, right? I'll call this sigma naught prime is minus 1, right? Actually, what will the two functions look like in that case? Of course, f1 looks the same. What will f2 be? Becomes 1, right? That will just look like this. Now you plot this, what is the sum of these two? f1 plus f2. It's just a shifted line, right? Okay, I have not drawn this very well, but it will basically be parallel to this. Okay, my drawing is bad, but you can go back and check it, plot it on MATLAB and check. Okay, so because of the weird way I have drawn it, I think, but what you'll get is, you'll get this to cross, okay, I'll plot it like this. It turns out that is going to cross, okay, now I see what the problem is, okay. It's going to look like this. Okay, let me put it this way. Obviously it needs to cross sigma naught equals minus 1. Okay. And what you'll see is, in general, if TD is greater than 0, you'll find out that sigma 1 prime and sigma 2 prime will be smaller, a more negative value than minus 1. Okay, you won't find the roots lying between 0 and minus 1. Okay. So, in general, you'll find it doing closer to or faster. So what that means is, right now we are looking at systems with small delays. Okay, next we'll look at what happens if systems have large delays. But what that means is, if you actually have small delays in the system, let's say in the feedback, your settling, your output settling can actually be faster than the case with no delay. Why do you think this is? Because what you're doing is, actually in this case there is no overshoot. Okay. In this case we are still not seeing the case with any overshoot. Okay. What you are seeing is, you are actually still accelerating, even though your error is decreasing, you are still accelerating for a little bit longer than is necessary in a first order system. Okay. That actually helps it to settle faster, a little bit faster. It is not so intuitive, I would say. Okay. It's not so intuitive, but this happens to be a property. Okay. Which is, if you add a little bit of delay, you can actually settle faster. Okay, in this particular kind of system. Sorry? Okay, we'll come to that. Okay, we'll find out what you need for overshoot and we'll slowly see. Okay, what will happen is, if you actually see a case where we are still dealing with a case which looks something like this. Okay, whereas the first order system would have looked something like this. Something much slower. Okay, we have still not seen, okay, case of overshoot. Yeah, right now we are still assuming zero input. No. Yeah, in this particular case, yeah, there is no case of overshoot, but we have just taken the sample case, right? But the general case is going to be an exponential. Okay, because remember, we did the same thing. We studied a steady, we assumed a steady state at the input, like a DC value or some constant value. Then we assumed that what will happen when you give slow speeds. We try to find out the bandwidth of the system. We said if the speed is slow enough, then it will follow the same case as a DC, right? We'll do the same thing here. Okay, it seems natural that we should do the same thing here. Okay, so this is something which comes out. So which means if you want to design a system with a fastest system, would have a little bit of delay in the feedback. Okay. Now, actually, first of all, this slight delay being a little bit faster, right? Do you find it similar to some case which you have seen before? Have you seen second order systems? You have seen second order systems before. What do you remember? What does this correspond to? The damping factor. Correct? If you have, and what do you remember from your damping factor? What value? If you plot your settling time versus damping factor, what does it look like? What is that eta equal to 1 called? It's your critical damping, right? This thing is similar to that, where you had a critical amount of delay. You can actually settle faster than a case where you have a single pole. Okay. Okay. So now, what happens if TD is very large? What is going to happen? What do you think is going to happen? We already know. We already know you are going to get, right? If you have large enough delay, you are going to get these kinds of overshoots and you are going to get these kind of oscillations, right? So what does that tell us? So that is when, beyond a certain value of delay, so what you'll find, we can do the same thing graphically. Okay. Okay, I'm going to copy this. Okay. So let's get rid of this case. We'll keep this one. I think that's okay. Okay, for large TD, it's going to look something like this, your exponential. Correct? It's going to be very fast, rising for less than 0 and decay very fast. So if you actually plot the sum of the two, so what is the sum of the two going to look like? It always, remember, it always has to pass through this point. Correct? So it's probably definitely going to be faster, approach the straight line faster because the exponential has decayed faster. What is going to happen here? It may actually never touch the x-axis. Okay? What is the critical damping? If you see, what does it correspond to? It corresponds to the case where it just touches the x-axis. You only have a single root at that point, or both roots coincide at that point. Right? And what happens? What solution will this give for sigmas? There is obviously no real solution. There will be complex solutions, which means oscillations. I mean, what means is you will have a sinusoidal component. Okay. When you try to solve for sigma for very large CDs, you will also get a sinusoidal component. That is the second solution. Okay. And so the general solution, remember, is a linear combination of the exponential and the linear combination of the sinusoid, right? And the sinusoid. It so happens when you have crossing the x-axis, the coefficient of the sinusoid is going to be 0. In the other case, you are going to get a sinusoidal solution. Okay? Okay, we'll come back to this in tomorrow's class. Actually, it won't. Okay, it won't. Okay, what the sigma not equal to 1 actually corresponds to a case where, for example, if you take a first order system, you can consider it as two poles. One pole is at sigma naught, the other pole is at infinity. Okay, or in this case minus infinity. Okay, you can consider a second order system with that, and that definitely is not the same as, because remember, this sigma not equal to 1, we got it from the point of crossing of the straight line, which is definitely going to be different from the point where the exponential crosses, touches the x-axis. It's definitely going to be different. Okay.